In the early days of fluid mechanics, before scientists knew about boundary layers, there was a paradox called Dalembert's Paradox, which was that calculations of inviscid flow around a cylinder, for example, showed that the pressure field was symmetric on each side, and therefore that there was no drag on the cylinder, whereas we know from experience that there is drag on a cylinder. So here we're going to start from inviscid flow, and then show how the existence of boundary layers resolves that paradox. So here I've plotted streamlines and pressure contours for the inviscid flow around an ellipse. At the front of the ellipse, this is the stagnation point. There is a high pressure. Around the equator of the ellipse, there is a low pressure. The flow is moving from left to right, so around the front of the ellipse there is a favourable pressure gradient, by which I mean that the pressure gradient pushes the fluid in the same direction as the flow. At the back of the ellipse there is another high pressure point, a stagnation point, and that means that around the back there is an adverse pressure gradient, by which I mean that the pressure gradient is pushing the flow in the opposite direction to the flow velocity. Now, although the viscous effects may be negligible in the free stream, all fluids obey the no-slip condition, and therefore a thin boundary layer forms around the surface of the ellipse. First of all, I'll draw the boundary layer in the region of the favourable pressure gradient. So here I'm plotting Vx as a function of y, where y is the distance perpendicular to the surface. And as we saw in the previous section, this boundary layer velocity profile is very steep at the surface. And this is because the pressure gradient is pushing the fluid in the same direction as the mean flow. It's rather like Couette-Poiseuille flow, in which the pressure gradient is pushing the fluid in the same direction as the mean flow. Now let's draw the boundary layer velocity profile in the region of the adverse pressure gradient. If the adverse pressure gradient is strong enough, it will cause the flow to reverse. So now let's consider the direction of motion of the flow just adjacent to the boundary. In the region of the favourable pressure gradient, it's moving in the same direction as the mean flow, but in the region of adverse pressure gradient, it's moving in the opposite direction to the mean flow. And these two flows collide at some point, and when they do, there's only one way for the fluid to go, and that's straight out. And at this point, the flow separates entirely from the body, and this is known as a separation point. Now in this diagram I've exaggerated that, but we'll see some photographs in a moment. So this flow separation completely changes the flow. It means that behind a body you have a region of separated flow, a recirculation region, in which the pressure is rather low, and this is what gives rise to the drag behind a bluff body. A bluff body is a body that has separated flow behind it. And this diagram here is taken from Frantl's original 1905 paper, where we see his diagram of the separation point, although I think locally this streamline should leave perpendicular to the surface. And so Prandtl's notes, a fluid layer which is set into rotation by friction at the wall pushes itself out into the free fluid, where it causes a complete transformation of the motion. And here are some examples taken from the excellent book An Album of Fluid Motion, where we can see the separation points. The top left flow is a flow around an airfoil. We see a separation point there and another one on the other side. The top right is the flow around a cylinder, and we can see a separation point here and one on the bottom. The bottom left is a separation point, what's known as a leading edge bubble, just at the leading edge of an almost rectangular object, and there's one at the bottom but you can't see it. And then we have a flow around a sphere where there's a separation point hidden under there, and one at the bottom as well.